Hello, everyone. I'd like to thank Five for giving me the opportunity to talk today about some industrial applications of surface chemical analysis. First, I want to acknowledge my coworkers, all of whom have contributed to various parts of this presentation. They include Mark Johnson, Christopher Young, Nitesh Madan, and Zheng Dong. First, let me tell you a little bit about what we do here at HP and Corvallis. Our main focus is on R&D for print technology, in particular thermal inkjet. And so inkjet started as this little printer here back in 1984 with about 90 nozzles on the print head. It's evolved over time to where you have a desk printer, something like this, perhaps at your desk, that has well over 2,000 nozzles per print head. And inks have evolved over time, so you get great photographs or just printing normal kind of business documents. But the technology that we use for TIG can be used in a number of other ways. One is 3D printing. One is to create bioassays with dispensing picoliter drops of known concentrations into assay wells, or another example is the web press, which is shown here. These printers can be placed in series, and you can actually effectively build a printer the size of your house. And so that's just some of the technology that we deal with here. One of the other things we, of course, deal with, and all of us do who are listening to this presentation, is the fact that pretty much what we work with, you can't see. And so you often get emails that have this kind of phraseology in them. And as we all know, we don't really want to use eyeball spectroscopy. So for example, this orifice plate that I'm showing here is made out of palladium, and it's also covered with Teflon, and you simply can't see that with your eyeball. So how do we use surface chemical analysis? We use it to answer questions that people have about their materials, to understand the chemistry, composition, understanding how different processes will affect the surface chemistry and what effect that has on the performance of a material. We have a lot of interaction with folks in our fab, looking at contamination, looking at process changes. We also deal a lot with polymers and the surface modification and or adhesion or adhesives. Adhesion in particular, looking at why things come apart and or why things stay together. The methods that we use are fairly commonly known, so that we use XPS, static SIMS, and Auger electron spectroscopy. Each of those techniques has pros and cons for doing and approaching an analysis, having to do with spatial resolution and having to do with chemistry and or quantification of the materials that we find on a surface. And of course, we have the obligatory stainless steel Christmas tree here, which happens to be one of the spectrometers in our laboratory. So I'm going to talk a little bit about different examples of doing surface chemistry and microanalysis. We all see things coming into our labs. People are asking, what's a spot that's present? What are the corrosion products? I need to characterize a process. I need to figure out a particle. You know, what is a particle? Where did it come from? Or there's an extra layer in my thin film and I don't know what it is and it really shouldn't be there. So we'll go through a few examples of that. This is an example of a polymer. This is an orifice plate on one of our products. And what they noticed was if you looked on the underside of this area right here, that there were spots, and they wanted to know what they were. And so we can take this sample put it into XPS system, and you generate a secondary electron image, the SXI. And you can see actually, looks like there may be a spot here. And those of you that deal with SXIs also know that you can see a lot of other things in this SXI which may or may not be related to differences in chemistry or composition. It's just a matter of sample charging. But in this case, when we go through and drop the beam on that spot and then look at an adjacent background area, what we find is that the spot is in fact tantalum oxide. And then we also mapped it, and the tantalum is present in discrete spots along the surface. And that actually gave our partner a clue as to where this was occurring in their process. Another common thing that we see in surface analysis lab, and you probably do as well, is someone has a bond pad. They're having wire bond issues to it, and they want to know what's the contaminant and why isn't this working and so on. I can tell you my experience is that about 95% of bond pad issues in terms of wire bonding have absolutely nothing to do with contamination. It's almost always the wire bonders not working right. However, you still get the sample, you still want to analyze it and be helpful. And so you can see in this optical image that there are areas that have different discoloration, and a partner described them as corrosion. It turns out they aren't corrosion. It turns out they are in fact different layers, different thicknesses of a carbonaceous layer that's on top of the bond pad. And you can see this in the spectra here. In these different areas, the inelastic background here changes rather drastically. And it's a nice illustration of what happens is you change the thickness of a layer and how the background changes. And in fact, the red one here is a very thick area, and the orange one is the thinnest of all of these. And so in this case, the background is actually moving back down as you add thickness. But it leads to the question of, so what is the thickness of the stuff that's on here, and how can we measure that? Now, there's different ways you can measure thickness. One is the obvious simple overlayer model, and where you have two peaks that are close together in kinetic energy. In this case, it's an oxide on top of metal. You can take the ratio of the peak heights, apply a correction factor, and come up with a thickness. Another similar approach to that is to use what Peter Kumpson calls a thickogram. And this is a nomogram of this same equation. And it's really good for peaks that are not close together in kinetic energy. And so it's a nice way to evaluate. It's the next step from the simple overlayer model, but the peaks are far apart. And you can get a fairly reasonable idea of what the thickness is of a material using this method. And of course, there's a two-guard method where it's a more holistic view of what the inelastic background looks like, and you can model that and come up with thicknesses. But there's other ways to measure thickness as well that we all commonly use. One is to do a sputter depth profile. And in this day and age of different kinds of ion sources, people will commonly use monoatomic argon. They may use C60. They may use a gas cluster gun like argon. Each of those has different utility for different material systems, and you can use them in combination to maximize their benefit. And another way that you can also look at thin films, which are not necessarily monolayer or nigh very close to monolayer, is to do something like an angle-dependent profile. And with the different photon sources that are available now, such as aluminum, magnesium, or zirconium, silver, you can, or chromium, you can look at different depths of a sample or look into a sample at different depths, and you can generate an angle-dependent profile, which is illustrated here. And this is what we most commonly see. working with your partner where you have a profile like this and then showing them a profile like this, the one on the right, is problematic because this is not really clear. Now, many of you are probably aware of this new software package from Phi, not advertising for Phi, but this Stratify actually converts this profile into this profile, and this is much easier to explain. And in fact, this is a profile of a 20 nanometer film of ALD hafnia, and turns out when we take this angular profile, we come up with something that's about 20 angstroms. I think I said 20 nanometers. It's 20 angstrom film. So this actually makes it fairly understandable. But going back to our bond pad, if I do an angular profile on this and then calculate what the thickness is, this comes out to be about 7 nanometers. If I use the nomogram method, it also comes out to be 7 nanometers. And so that's a nice way to sort of corroborate what we think it is, what you estimate it is from looking at the spectra initially, and then doing the two calculations, you come up with an answer that seems about right. Is it good to 5 decimal places? No, but apparently to stratify, you can really, it's amazing what computers do. Anyway, but measuring the thickness of an oxide or an overlayer can be used a number of different ways. And this is an illustration of where we used it to characterize an asher. Ashing means something different to almost everybody that's sitting at the table when you mention that process method. In this case, I'm going to describe ashing as using an oxygen plasma to oxidize carbonaceous material into volatile components, and then they will leave and hence clean the surface. But in this case, what we did was use some palladium orifice plates, and we would put them in the asher, and an effect of the asher, of course, is to oxidize the palladium. And what we were looking at was how was the asher working across from left to right and then from front to back? Were all the shelves giving you the same results, and was there any difference? Because if you ever have the opportunity to look through the window of one of these ashers, it's kind of like the aurora borealis, that there's sort of this cloud of plasma floating around. Well, is it uniform everywhere? The answer is, if we take the ratio of the palladium oxide and palladium metal, it is not uniform throughout the asher. And in fact, from side to side, you see variation, and from front to back, you see variation. So this gives us a way to actually characterize what's going on and maybe optimize different parameters. There's another way, though, that you can also look at the effects of ashing. And in this case, what we're using is, the way we did that was to use tape and what we call a die carrier assembly. So our TIG die is on the top of this, and the bottom looks like this. So these are the slots where ink will come in and get to the top of the print head. But the question was, with the plasma process, does the plasma go down inside through the nozzles of the print head, and then how far down inside does it go? And in this particular case, we were using a tape that actually had silicone on it. So you can follow the oxidation of the carbon, or you could follow the oxidation of the silicone, which turns into silica. And you can see that, in fact, there is oxidation that occurs down inside, that the plasma does go through the DCA down to the tape. It's more effective, obviously, outside than it is underneath, but nevertheless, you still have the effect. And there's two different ways, of course, you can measure that, either by the amount of silicone and silica, or by the oxidation of the carbon. So then the other kinds of analyses that we're asked to do, this is a common one. This is what's the residue? And in this case, there's a residue left on part of the die, and you can see it's a fairly small area. And a common way I mean, the first stop going into almost any analytical lab, and certainly one like ours, your first stop is going to be in the SEM lab or in the IR lab. Um, Most likely this is an inorganic contaminant, so SEM is an obvious good first choice to take a look at it, which is what we did. And what you find is, and it's easy enough to, of course, turn your EDS system on and take a look at what that is. So you map out these different elements that you've detected with the EDS, and you find that the majority of what you're looking at is carbon and silicon and minor components of oxygen and nitrogen, and they also say there's a trace of aluminum. But we take this sample down to the OJ because your analytical volume is quite different. You're looking at something different than what we were looking at with the EDS. And in this case, what you find is if you look at this collection of particles that ends up on the edge of this die, you drop the beam on that, on the particle, you drop the beam also on the substrate area here, and you find that in fact they are quite different. And the area of the particles is in fact silicon dioxide, and the area in the substrate is silicon carbide. It happens that, you know, most of the time we don't think about electron beam Auger as being a great way to differentiate chemistry. Silicon is one of those magic elements that you can in fact differentiate the chemistry, and there's a couple different ways that you can do that. One is by the peak position, which changes between, in this case, oxide and carbide. Also, this structure here, which is part of the Auger series, also changes relative to the oxidation of these two materials. So in that case, what we could clearly identify was that these particles were silica, and based on that, the partner could go back to their fab process and figure out that one of their etch tanks was contaminated with particulate matter, which happens to be silica. So looking at small areas, again with electron beam Auger, this is an example of a 3D printed piece of steel. So part of our technology portfolio is to 3D print metals, and in this case, it's stainless steel. And one of the most common uses of electron beam Auger, when back in the old days, if you will, was to look at metallurgical samples. And in this case, what we're doing is looking at cross-section that has some inclusions. And so we can zoom in on these and you can see there's some particles here. And the question, of course, what is it and where are they, and how do things fill in? And we find that there's copper here, and we can map these, copper and iron. There's niobium in this particular flavor of steel. And you can map them out and see what's present and where it is spatially. So the niobium is not actually obvious in this particular micrograph, but it's clear in the Auger image. Likewise, you can see there's actually sulfur also across this particular inclusion. I'm going to finish up with an example, an uncommon example of a synergy between static SIMS and Auger spectroscopy. And that is, we've learned that using the GCIB, of course, is a great way to look at polymers and organic material in the static SIMS. The other part of using GCIB is it selectively removes organic material and leaves behind inorganic material. And so what we're looking at here is a resistor that has a residue left on it. Turns out it's basically burned organic material. However, we can remove that. When we do, we find other components of the ink that have separated out spatially on the surface. And the SIMS, of course, is not necessarily quantitative. And that's one advantage, and I use scare quotes to say that we can quantify what we're seeing in the Auger. But if you look at it, if you look at the SIMS image, you can see there's a distribution of iron and there's copper and calcium. Those are all components of that particular ink. If you look at it with the Auger, where we've removed all the organic contamination and left behind the inorganics, you can see we have the bathtub ring of iron here. This plate is called an anti-cavitation plate. It's made out of tantalum. We map the tantalum for completeness, and we see they actually leave some holes. And so this is one of the reasons you do image maps, right? So that you can determine, have you filled in everything? Well, if you overlay these maps, you see there's some gaps like here. Drop the beam in there, and what you discover is that there is in fact chromium present. And now we can map out the chromium, and we can map out the tantalum, and we can map out the iron and see how these are distributed. And that actually gives us information about the fluid dynamics of the ink inside the firing chamber here. So that's of great interest. Finally, I hope I've been able to tell you a little bit about how we've used surface chemical analysis on a variety of the material systems that we see coming through our laboratory. We get information about composition, chemistry, thickness, and of information about particulates and or contamination. I have a picture here of my colleagues in the analytical and development lab. Great bunch of people to work with. And with that, I thank you for your attention.